A piston in a water pistol drives water through a 0.9 centimeter radius tube into a tube of radius 0.9 millimeters. If the pistol is shot horizontally 2 meters above the ground and the range achieved is 10 meters, what is the exit velocity of the water from the pistol? A. B. What is the corresponding plunger speed? C. What is the nozzle pressure? D. What is the pressure in the large cylinder? E. What is the required trigger force? To find the exit velocity, we can first of all find the flight time using h is equal to 1/2 gt squared, solving for t. T is equal to root 2h over g. The water will spend 0.632 seconds in the air, and then the exit velocity v2 from the water pistol can be calculated as the range 10 meters divided by the flight time, so that's 15.8 meters per second. For B, to find the corresponding plunger speed, we can use the continuity equation, a1v1 equals a2v2, solving that for v1. The plunger speed gives us v1 is v2, the speed that we just calculated, exit speed of the water from the pistol, times the ratio of the two areas. A2 is the small nozzle area, 0.9 times 10 to the minus 3 meters, 10 to the minus 3 meters is a millimeter, divided by 0.9 times 10 to the minus 2 meters, 10 to the minus 2 meters is a centimeter. This now will give, the 0.9s will cancel, we'll get 10 to the minus 6 over 10 to the minus 4, which is 10 to the minus 2, and so that's going to be 10 to the minus 2 times 15.8, which is 0.158 meters per second. Quite a bit slower. Okay, C. What is the nozzle pressure? Well, the pressure at the nozzle, it's exposed to the atmosphere, so the pressure at the nozzle, P2, is equal to P atmosphere, which is 1.01 times 10 to the 5th Pascal. What is the pressure in the large cylinder? Okay, well, the pressure in the large cylinder we can get from Bernoulli's equation, P1 plus rho GH1 plus 1/2 rho V1 squared is equal to P2 plus rho GH2 plus 1/2 rho V2 squared. So P1 is equal to P2, which is P atmospheric, plus rho GH2 minus H1 plus 1/2 rho V2 squared minus V1 squared. Okay, so that is 1.01 times 10 to the 5th Pascal, that's atmospheric pressure, plus density of water, 10 to the 3rd kilograms per cubic meter, times the acceleration of gravity, 10 meters per second. Okay, so I need some estimate for H2 minus H1. That is the height that the nozzle is above the trigger. Let's assume 5 centimeters for that. And so this would be 5 times 10 to the minus 2 meters. That's a fairly realistic assumption. And then this last term is going to be plus 1/2 times the density of water, again, kilograms per cubic meter, and then times V2 squared. So in other words, that's 15.8 meters per second squared minus 0.158 meters per second squared. Okay, now if you look at this, you'll see that this term here 10 to the 4 times 10 to the minus 2 is 10 to the 2. 5 times 10 to the 2 is completely negligible compared with this. And we'll find that this term is roughly atmospheric. So if we put all three terms in, first term, atmospheric pressure, plus, as I said, 5 times 10 to the 2 Pascal. This is very small compared with that. And then the last term, calculated it out, is 1.25 times 10 to the 5th Pascal. And so what I'm going to do with that middle term is just ignore it. We'll ignore that term. And so the total pressure I get is 2.26. Okay, last part now is what the force required on the trigger is to drive the cylinder in, cylinder of area A1. And so the P1 is pressure. I'll just say pressure is equal to force over area, and therefore force is equal to area times pressure. Now the important thing to understand here is the pressure here is the gauge pressure. That's what matters. It's this pressure, the portion of P1 that's above atmospheric, which is going to be this term right here, times the area of the cylinder. And so the force required is going to be the area of the cylinder. The area of the cylinder is pi r squared. That's pi times the radius is 0.9 times 10 to the minus 2 meters squared, times the gauge pressure, 1.25 times 10 to the 5th Pascal. And that calculates out to be 31.8 newtons, the force required on the trigger.